So hello everyone, and welcome to video 6.3.2, where we're going to go ahead and finish off our lesson 6.3. So in this section, we are going to do the last idea and 3 parts of an example. So idea number 5, the value of the equilibrium constant changes with the temperature. That is key right there, because the free energy of the system will change. Now we can use the same formulas to determine the values of KQ and delta G reaction, and we'll do this at different temperatures. So for example 2, we're going to consider this reaction for the whole video. So 2SO2 gas plus O2 is in equilibrium with 2SO3. And we're given our delta H reaction, delta S, and then we are given our delta G reaction. Okay, so calculate the value of KQ at 25 degrees Celsius. I'd like you to please pause the video and try part A, and then come back to check your work. Okay, welcome back. So for this one, we're going to write down our formula first. So KEQ equals E to the negative, and we're using this formula up here, the one that we memorized or derived, E to the negative delta G naught reaction over R times T, right? So that's the same formula. So the only thing I need to do in this case is plug it all in and make sure that my units and my signs are taken into account. So E to the negative, and then my delta G reaction is given to me up at the top right here. So negative 142 kilojoules. And then I'm going to need to get into joules because I want to be able to cancel my units. So I'll just convert those right in line. You could, of course, just have put in 0.142, or sorry, 142,000 rather, joules per kilojoule, times 8.314 joules over moles times Kelvin. So here is the ideal gas constant, that's the R, and that's given to me way up top. And now this is the reason you can see right here I need it to be in joules, so I can cancel those out or have them match. And then finally the T temperature, 25 degrees Celsius, needs to go to Kelvin, so that's 298 kelvins there. Okay, so my kilojoules, let's do our unit conversions here. So kilojoules cancel out there. Joules as well. And let's see, our kelvins will cancel out. And we're left in per mole. So my E, my KEQ, is E to the 57.3. Plugging that in, I get 7.8 times 10 to the 24th. And that's my new KEQ. It's huge at 25 degrees Celsius. Now we're going to compare. So say we increase the temperature from 25 to 100 degrees Celsius. What's KEQ now? So here we're going to assume that the enthalpy and the entropy don't change with temperature. It's not technically true, but we're going to assume that for this case. So please pause, go ahead and attempt this problem, and then please come back and check your work. Okay, welcome back. The first thing we need to do is calculate delta G, and delta G equals delta H minus T delta S. Plugging everything in here, for my delta H, I have negative 198 kilojoules per mole, and subtracted from the temperature, 100 going to Kelvin is 373 Kelvin. The change in enthalpy was given to me at negative 187 joules over moles times kelvins. And I need to get from joules to kilojoules in this case, so I can make my units match. And 1 kilojoule is the same as 1,000 joules. Okay, plugging all this into your calculator, you end up getting negative 128 kilojoules per mole for your delta G. Now that's not what we were trying to calculate. We were trying to calculate KEQ. And so we just needed to get delta G for KEQ, because remember, it's not at standard state anymore, so we can't use the delta G naught that was given to us up here. It's going to be different, see? Negative 128 versus negative 142, because our temperature is different. And standard state assumes 25 Celsius. So our new KEQ is going to be equal to E to the negative delta G reaction, and not at standard state this time, because again, different temperature, over R times T, plugging it all in. What we calculated, negative 128 kilojoules per mole converting kilojoules to mole, or to joules. Plugging in our R, which is our ideal gas constant. And then our temperature, remember 100 Celsius is 373 Kelvin, because we add 273 to our temperature there. Oh, don't forget the division sign. Where did that delta G reaction over? Let's see, RT. So we're going to put our division sign here. Sorry about forgetting that. And so our KEQ now is going to be equal to 9.13 times 10 to the 17. And we can see how different that is. Look how much that changed from just increasing our temperature by 75 degrees, right? From 25 to 100 degrees. Now, at what temperature would this process be non-spontaneous at standard state? So at which temperature is it not going to go forward anymore? So for this, you're going to need your delta G to be greater than 0. So I want you to please pause and just set up the equation and then come back and check that your equation's correct. Okay, welcome back. So let's look at our equation. So delta G equals delta H minus T delta S. And all of that is going to be greater than 0 because we want our delta G to be greater than 0, right? And so if we just kind of get rid of this middle part right here, we can see when delta G is going to be greater than 0, it's going to be non-spontaneous. Now we can, instead of having delta G, we can sub in or substitute delta H minus T delta S, which is greater than 0, and that is what we're going to use for our equation. Now we have an inequality. So please pause the video, plug in your numbers, and then come back and check your work. Okay, welcome back. So our delta H is negative 198 kilojoules per mole minus T. And we don't know the temperatures. We're trying to look for the temperature. Plugging in our delta S, negative 187 joules over mole times Kelvin. And then getting rid of joules and getting into kilojoules, 1 kilojoule, because we want to match our units over here. As long as your units match either way, you're okay. You could have converted that to joules as well. It doesn't really matter. 1,000 joules. And all that's greater than 0. So I want to go ahead and start rearranging this. So I want to add 198 to each side here. And when I add 198 to each side, get rid of this one on this side. This side will have plus 198. I'm going to end up with 0.187 T. That's going to be greater than the 198 I added to both sides, just using algebra. And I just got rid of all my units here so it's not so confusing. I'm going to isolate T, so 0.187, 0.187, and T is going to be greater than, let's see, 10,000 or 1,058 Kelvin. So our temperature needs to be greater than 1,000 to make this non-spontaneous in the forward reaction. Okay, so that is it for video 6.3.2, and that is it for Unit 6, and I will see you next time for Unit 7. Good work, everybody. Bye.